All right, chemists, welcome back. Today we're going to be starting chapter 18, acids and bases. Today is just going to be a general overview. What is an acid? What is a base? We're going to get into some of the properties, looking at some names, things like that. Okay? So, as usual, we've got our learning objectives here at the top of the note packet. Okay, so by the end of this unit, we should be able to do these things. All right, so let's get started here by looking at some properties of acids and bases. Okay, so starting off with some acids. Okay, some of the main properties that we need to be aware of, be able to identify acids by, right, we have here. Number one, acids have a sour taste. Okay, so we have a lot of acids in the foods we eat. Things like any kind of citrus, oranges, lemons, grapefruits, they all have citric acid in them. Okay? Other things would be things like vinegar. All right? Vinegar has acetic acid in there. Right? We use that for our cooking as well. Right? And one other one would be something like vitamin C. Okay? Those all have acids in them. Right? And they all have that very characteristic sour flavor to them. Okay, when I react acids with metals, right, they will dissolve metals. I'll get more into that here in a moment. Okay, but the key thing is they will react with metals. Most bases do not. Okay, acids also have the ability to conduct electricity. Right. That's because they are electrolytes. Right? And if you recall from our discussion on ionic compounds are electrolytes because when they dissolve, they break up into ions. Right? And it's those ions that carry the charge. Okay? So the more ions in the solution, the better that charge is going to be carried, right? And the brighter your light bulb is going to go, for example. All right. Another good way to tell if I have an acid is using a test called the litmus test. Right? Litmus is something we call an indicator, just tells us whether something is acid or base. Okay, we have blue litmus paper, right? So it's literally it's blue, right? And if I dip it into an acid, that blue litmus paper will turn red. Right? Likewise, if I have some red litmus paper and I dip it into a base, right, they'll turn blue. Okay, so remember, acids are red, bases are blue. Right? And kind of going along with our one above with acids dissolving metals, okay, when acids react with metals, right, they're going to have a very specific reaction. Okay, so let's look at what that reaction is. Down here I got zinc reacting with HCl. Okay, so zinc is my metal, HCl is my acid. Okay, and this is a single replacement reaction. Hydrogen, right, it's hanging out with the metals over there on the periodic table. Okay, so it will behave like a metal in this case. Okay, so zinc is going to displace the hydrogen. So hydrogen comes out by itself. All right, I'm going to put zinc with the chlorine. Now I'm going to double check, make sure my formulas are correct. All right, hydrogen I know is diatomic, so I'm going to put H2. All right, and then look at the zinc chloride. Zinc, we got to remember that is one of my transition metals that always makes a +2 charge. All right, chlorine on the periodic table makes a -1 charge. So to balance things out, I need to have 2 chlorines here. All right, and I could get rid of, don't want to get rid of the whole thing. There we go. Okay, so now my charges are all balanced out, got the proper formulas. I can go back, I can balance out the whole reaction. I'm going to put a 2 in front of that HCl. Okay, so anytime I have a metal plus acid, like I have here, I'm always going to be forming hydrogen gas and some kind of a salt. The salt in this case is another term for an ionic compound, right? Like so ZnCl2, right? This is not table salt, but it is a salt. Okay? So we have that reaction, right? But we also have the reaction between carbonates and acids. So I've got sodium bicarbonate here, right? So there's my carbonate, the CO3, right? So this is baking soda, right? And H2's, HC2H3O2, this is acetic acid. This is the main component of vinegar. Right, so a lot of you guys have probably done this experiment before, either at home or maybe in kindergarten class. Right? If you take vinegar and baking soda, you mix them together, you get a baking soda volcano. Right? It'll start to, foam up, it'll erupt like a volcano does. Pretty cool. Kids love it. Okay. So if I look at this one, this is actually a couple of reactions in one. All right, so I'm going to break it down first. Okay, we have two ionic compounds. So this is going to first be a double replacement reaction. Okay, so I'm going to start by taking my sodium. I'm going to pair that up with my acetate. Okay, so we're going to get sodium acetate. Okay, sodium is +1, acetate's -1. Right, so they are going to be just fine there. That's my proper formula. Okay, then I've got my hydrogen and I've got my bicarbonate. So bicarbonate, it's a -1 charge, hydrogen's a +1 charge. So they're going to come together and give me carbonic acid, H2CO3. Okay, so there's my first part. Okay, double replacement reaction. Okay, but the issue here is that carbonic acid is not very stable. Okay, so this carbonic acid is going to further undergo another reaction. Right? It's going to decompose, right? And it's going to decompose into carbon dioxide. Right? And what's left? 2 hydrogens and an oxygen. So we're going to get water. Okay, so that carbonic acid doesn't last for very long. Like pretty much as soon as it forms, it decomposes. Okay, so really, what we're making is we've got the sodium acetate, right, a salt, right, and then we're going to have the carbon dioxide and water. Right, so we don't have to do that step there with the carbonic acid. We just go straight to saying it's going to make CO2 and H2O. Right, so anytime we have a carbonate, okay, like we have over here, okay, react that with an acid, we're always going to get some kind of a salt, some kind of ionic compound, plus carbon dioxide and water. All right. So those are the main properties of acids. So let's take a look at some acids. Okay, we have some common ones here, right, along with their names. Right, if you look, you'll notice that all of the acids that are listed here, they have hydrogen in front. Okay, majority of acids are going to be written this way: the hydrogen first, right, and then the rest of the molecule. Okay, one example where that might not be the case, you might come across be like this acetic acid. Right? Sometimes you'll see it written like it is here, or the HC2H3O2. But another common way of writing it out would be CH3COOH, right? And that COOH, that's another way of indicating this is a certain kind of acid. We call it an organic or carboxylic acid, right? And instead of that hydrogen being in front, right, now we have the hydrogen at the end, okay? But if you see either one of those, right, if the hydrogen's in front, right, we know it's going to be an acid. Or if we see this COOH, it has to be very specific. It has to be that COOH, right? That would also tell us we have an acid. All right, now let's take a look at the names that are given to us here. Okay, let's start off with the ones that have, essentially polyatomic ions, right? I've got SO4, it's sulfate. And I got nitrate, acetate, nitrite. Okay, if I come over and I look at these, let's look at the NO3 one. Okay, so we have the nitrate ion there. Okay, so if I have my polyatomic ion, if it ends in ATE, right, to get the proper name of the acid, what I'm going to do is I'm going to drop the 8 and I'm going to replace it with ic. Right? So nitrate becomes nitric, and I'm just going to add acid to the end. Okay? Acetate becomes acetic acid. All right? Compare that to my NO2. This is nitrite. Right? If my polyatomic ion ends in ITE, I'm going to change the ending to OUS. So instead of nitrite, it becomes nitrous. And then again, I'm going to put the acid at the end. Okay, so a good rule to remember is I ate something icky, right? So ate goes with ick. So I ate something icky. Now my stomach is upset, right? There's not really a good rule to remember the ite to us. Okay, if you can come up with one, let me know. Okay, but ate goes to ick, ite goes to us. All right, but that leaves us with two other ones. We got the HCl up top and the HF. These ones don't have polyatomics. Okay, so when I don't have a polyatomic ion, what I do is I always start off by putting hydro for the hydrogen part of it. All right, and then I'm going to use the base of the other part of my acid, right? And then I'm going to finish it off with ic acid. Okay, so I got hydrogen and fluorine, so I'm going to have hydrofluoric acid. All right, or up here, I'm going to have hydrochloric acid. Okay, likewise, if I had HBr, right, this would become hydro. Root is going to be brome, and I'm going to do ic acid, so hydrobromic acid. Right. Similarly, HI is going to become hydroiodic acid. Right. Last one to draw your attention to is that H2SO4, okay, doesn't exactly follow the rules here, right? We got sulfate, so it should be sulfic acid, okay? But that doesn't quite run off the tongue nicely here. So, we do add in that extra syllable, right? We call this sulfuric acid, right? But if I had H2SO3, this would be sulfurous acid. Okay, so some of them, you just got to kind of learn like what might be a slight little tweak. Okay, but by and large, you've got a polyatomic, you got the eights go to ic, the ites go to us, right? And then add the acid at the end, right? And if you have just one thing with hydrogen, it's going to be hydro, root, and then ic acid. All right. So flipping on over. Okay, we already talked about how the acids, they all have hydrogen in common. Okay, so what that means then is that when I take that acid, if I were to dissolve it in water, right, like we've got here, okay, all of my acids, they're going to dissociate. Remember, that's a fancy way to say they're going to break up, right, into H plus and then whatever's left. Okay, so for example, if I have HCl, okay, that's going to break up. I'm going to get H plus and then Cl minus. HF is going to break up into H plus and F minus. HNO3 would be H plus and NO3 minus. Okay, so that's one of the key things. When they dissolve, right, they're going to break apart into that hydrogen ion and then whatever is left behind. Make sure you get those charges in there, right? Can't forget about those. All right, let's talk a little bit about bases. Okay, bases we don't use for food as often, okay, because bases tend to have a bitter taste to them. Right, but there are some notable things that we do use, like coffee, chocolate, also like almonds before they've been roasted. Right, they tend to have a bitter taste to them. Okay, so bases, they have that bitter taste. Okay, they're also going to feel slippery if you get them on your hands, kind of like you got soap on your hands, because that's literally what's happening. Is the base is reacting with the fat in your skin, right? And it's turning you into soap. Okay, and that's why it feels kind of slippery, right? That's how we make soap. We take fat and base, right, and they'll make a soap. Right? We already talked about litmus paper. Bases, like we said before, they will take red litmus paper and they will turn it blue, right? So blue's for bases, red is for acids, right? And just like acids, bases have the ability to conduct electricity. Again, that's because they're going to be forming ions. All right? I'm also going to put on here that bases, like acids, are corrosive. All right, so if you get some on you, it's going to burn your skin, right? Acids are going to do the same thing, right? We use bases for things like drain cleaners, right? Like if you have a clog in your drain, you pour some liquid plumber or some Drano, right? Those tend to be made out of strong bases, right? Because they are corrosive. They'll break down wherever that clog is, right? And hopefully get it to flush through the pipes. Okay, so let's look at some common bases. Okay, we have things like sodium hydroxide, right, NaOH. We have potassium hydroxide, KOH, right? So a lot of bases are going to end with that hydroxide ion, right, OH minus. Right? But not every base is, okay? Some things like sodium bicarbonate, right? Baking soda, that's a base, but there's no OH minus there, okay? If we got that carbonate ion, right? So this is like a carbonate base, okay? And probably the most important one that doesn't quite look like the others is ammonia, okay? This one, you got to remember the formula, NH3. Ammonia doesn't look like our other bases, right? But it is indeed a base. Okay, so similar to acids, when I put a base into water, it's going to break apart. It's going to form some specific ions, but this time, instead of H plus, bases are going to make OH minus. Okay, so for example, take my NaOH. And that one's pretty easy. I'm just going to break it up into Na plus and OH minus. All right, potassium hydroxide, KOH, breaks up into K plus and OH minus. All right, ammonia, this one's a little bit different, right? Because I don't have that OH in there. Okay, so what I'm going to do is I'm going to add in some water. Right, and what's going to happen is I'm going to form the ammonium ion, H4 plus, and what's left behind for my water is going to be my OH minus. Okay, so I'm making those OH minus ions here. That's what's making these guys a base. All right, let's flip on over. All right, so one of the things we have to be able to do is identify, is a reaction acidic, basic, or neutral? Okay, and it has to do with those ions that are being formed, those H pluses and those OH minuses. Okay, so before I get into defining what exactly acidic, basic, and neutral is, all right, let's come down here to this equation with the waters. Okay, if I have pure water, right, just water molecules, nothing else, those water molecules will undergo a process called autoionization. Okay, where they're going to react with each other and they're going to form ions, kind of automatically, right? Hence autoionization. Okay, so what's going to happen is one of these water molecules is going to give up an H plus to the other one. Okay, so the one that gains a hydrogen, instead of being H2O, now it's H3O, and it's got that positive charge, right, because it's H plus. And then the one that gave up the H plus, so now it's going to, instead of being H2O, it's only one H and an O. Okay, and because I lost the positive charge, now it's going to be negative, so I've got hydroxide. Okay, so I've got my hydronium ion, and I got my hydroxide ion. Okay, so long as those two ions are balanced out, we're going to have a neutral solution. Okay, and in pure water, that's what we should have, right? Because just look at the stoichiometry, right? I'm taking two neutral water molecules, right? Every time I do this autoionization reaction, I'm going to get one H3O plus. And for every one of those I make, I'm also making one OH minus. Okay, so because I'm getting one and one, right, they're going to cancel each other out, right? We're going to remain neutral. Okay, now, little aside here, chemists are lazy. Fully, I will admit that. Okay, and I don't always have to put that water in there. Okay, so a lot of times we will see things in acid-base chemistry without the water because we understand that the water is there, okay, but we don't always want to write it in because sometimes it makes things too messy. It can make things confusing, okay? So that same autoionization reaction we're just looking at, we can write it out with just one water molecule, and instead of saying one is donating a H plus, one's taking that H plus, we can just say it splits apart. I'm going to get H plus and OH minus. Okay, so in this case, I'm saying that H plus is the same as that hydronium ion. Okay, because we are understanding that this is taking place in water, right? So there are other water molecules around that would be taking up that H plus and making that hydronium ion. Okay, but I don't want to write it all in there. Okay, so I'm being lazy, and I'm just going to call it H plus. Right, so I can use those two things interchangeably. Okay, so we said down below, so long as my H plus and my OH minus are equal, that's going to be neutral. Okay, so if my concentration of H plus or H3O plus is equal to my concentration of hydroxide, I have a neutral solution. When those start getting unbalanced, that's when we start getting acidic and basic. Okay, in an acidic solution, my H plus concentration is going to be greater than my OH minus concentration. Likewise, my basic solution, the H plus concentration, is going to be less than my OH minus concentration. Okay, so depending on which one I have more of, that determines whether my solution's acidic or if it's basic. Okay, so coming on down here, I just got a couple of definitions that we need to go through here. Our original definition for acids and bases is the Arrhenius definition. Okay, this one's very specific. We don't use it very often, but an acid is going to produce that H plus, and it has to be in water. Bases are going to produce that OH minus, and again, they have to be in water. Okay, so we don't use this one very often because you saw before, not all of my bases are going to have that OH minus, right? And we're also not always going to be doing things in water. Majority of times, yes, we will, okay, but it doesn't always happen. So we need a broader definition. Okay, that's where our Brunstad-Lowry definition comes in. This came later, right? It's a more broad definition here, right? And our acids are what we call proton donors, and our bases are proton acceptors. Okay, so what's a proton? Right? Well, let's take a look here. I got hydrogen, right? A hydrogen atom. Hydrogen atom is one proton and one electron. Right, if I remove that electron, make it a hydrogen ion, H plus, now I got 0 electrons, but I still have one proton. Right? And that's all that I got. It's just that one proton. Okay, so when I talk about proton donor, proton acceptor, I'm really talking about H plus donor or H plus acceptor. Okay, so we're moving that H plus back and forth. All right, so let's look at a couple of examples. Okay, so I've got HCl plus H2O. making hydronium and Cl minus. Okay, so if I look at this, what's going on here is my HCl, I am losing H plus to that H2O. Okay, so the H2O is gaining H plus, it's accepting. So that means H2O is my base. And HCl, it's losing that H plus. Okay, so it's going to be leaving behind that Cl minus. So since I'm losing, that's my acid. Right? If I have an acid, I got to have a base. Right down here, excuse me. Okay, what we have going on here is now it's going the opposite direction. My water is giving H plus to the ammonia. Okay, so I'm getting NH4 plus and OH minus. My water, since it's losing H plus, that's my acid, and H3 is my base. Okay, now, if you notice here, okay, water is doing something special. Okay, up here it's behaving like it's a base. Down here it's behaving like an acid. Certain molecules can do that. They can be either an acid or a base depending on what they're with. We call those molecules amphoteric. Right? It just means it can behave like an acid or a base. Right? The last thing here is the conjugate acid-base pair. Okay? These are going to be two substances from a acid-base reaction that are going to be related by the transfer of a proton. Right? Whether that's one's picking it up, right, or if it's losing that proton. Okay? So key thing is an acid always transforms into what we call the conjugate base. Right? And the base is always going to be paired up with the conjugate acid. Right? Note that it changes. Okay? So if I come back up here, right, to our reactions, let me clear some stuff out here. Okay, so I'm starting off, I got HCl. And what I'm going to do is I'm going to first pair that up with the thing on the product side that looks the most like that. So HCl looks to me most like Cl minus. So I'd say they're an acid-base pair. Okay, H2O and H3O plus, they look pretty similar as well. Right, now we already said this was my acid, this was my base. Okay, so my acid, when it loses a proton, right, it becomes the conjugate base, right? Whatever's left behind is the conjugate base. Right, my base, when it picks up a proton, it forms the conjugate acid, right? A good way to think about this is it's an acid now because H3O plus has an extra hydrogen that it can easily donate, right? It can easily get rid of. Okay, Cl minus doesn't have any hydrogens, right? So what it can do though is it could pick up an H plus, so that would make it a base. It would be an H plus acceptor, a proton acceptor. Right? Why don't you pause for a moment, try and identify our conjugate acid and conjugate base here in this equation. Okay, so we already said that NH3 is my base, water is my acid. Okay, so NH3 looks a lot like NH4 plus. Okay, so to go from NH3 to NH4, I got 3 hydrogens to 4 hydrogens, so I've added or I've accepted a proton. So that makes this my conjugate acid. And water is most similar to OH minus. Right, so my acid becomes my conjugate base. Okay, so last thing here is you got to make certain here that these guys only differ by 1 H plus. Okay, so for example, HCl and Cl minus, right? They differed from an H plus. I took away a proton, right? Or HNO3 and NO3 minus, okay? If I have something like H2SO4 and SO4 2 minus, that's not a conjugate acid-base pair because they're differing by 2 hydrogens. Okay, I could do H2SO4 and HSO4 minus. That would be one conjugate acid-base pair. Or I could do HSO4 minus and SO4 2 minus. Right? Both of those are differing only by a single hydrogen. Okay, so that makes them conjugate acid-base pairs.